we shall see that in order to unlock the needed flexibility for large-scale integration of renewables like wind and solar power, we need digitalized energy systems, AI and grey box models, a description of the flexibility, new digitalized energy and electricity markets, and finally forecasting, IoT and control technologies. In this lesson and lesson number 6, we will address these topics. For a power system, the energy production and consumption have to be balanced in real time. Due to the complexity at the end user side, this has to be done by extensively use of digitization, artificial intelligence, AI, and the flexibility is activated by the use of control and IoT devices. EU has introduced a new concept called the SMARTNESS Readiness Indicator, SRI. This is a method by which a building can be characterized with respect to smartness based on information about the building and installations, like for instance the heating system. The method is based on tables with information on how various elements can contribute to the total smartness. The method applies only to buildings. However, in the future, a lot of the flexibility has to come from water handling, industry, mobility, and sector coupling. Furthermore, for real-time applications, we need a method which is based on data or evidence. And in this lesson, we will introduce the concept of a flexibility function and a flexibility index. These are concepts which have been developed internationally within IEA, more specifically within EBC Annex 67, and which can be applied to all flexible units and on all aggregation levels. Related to classical market theory, the flexibility is characterized by the slope of the demand curve. This is a single value, which is called the price elasticity. However, if for instance a supermarket has been flexible for the past 15 minutes, it might not be able to be flexible for the next 15 minutes, simply due to constraints on the temperature of, for instance, the displays with milk. Consequently, the flexibility has to be described dynamically. To activate the flexibility, we need an activation signal. A suitable activation signal in general and specifically for integrated energy systems is a real-time price signal. The figure here shows the response obtained using data from PNNL's Olympic Peninsula project for a small group of buildings. In the figure, the response to a step change in price is estimated, and it shows how the power consumption is reduced in a period up to 5 hours, and following this period we see a small rebound effect. Within the scope of the AEA working group, these principles have been generalized. In effect, the flexibility function is described by a so-called flexibility function, which simply is the expected demand as a function of a price signal. For linear systems, the flexibility function can be depicted as a step response function as shown in the figure. Let us now consider the use of flexibility functions for providing ancillary service solutions. The flexibility function characterizes the flexibility of a given smart unit, a building, wastewater treatment plant, supermarket, etc. Given the flexibility function, we can easily find the controller which generates the price signal that leads to a requested response. And as a result, we are now able to control the electricity load as well as related states like the voltage level. Basically, a controller can be formulated for any wanted load profile, like load balancing, or any needed net-related ancillary service. As an example, we are now able to generate prices that can be used for peak shaving or congestion management. A classical approach would be to bid flexibility into a market, for instance for solving voltage issues in a DSO grid. However, in order to solve all such ancillary service problems for all nets, we need a huge number of markets. For a small area in Germany, they calculated that they would need around 6,000 markets. And furthermore, the liquidity of each market would be very limited, and it would be difficult or impossible to operate all these conventional markets. Instead, using the concepts of flexibility functions, controllers with price generators can replace such low-level markets. By using the concept of composite pricing, we will be able to solve all balancing and ancillary service issues by just a single price to the customers. This will be described as a part of the so-called Smart Energy operating system in lesson number 6. In fact, other type of penalty signals can be used. Let us, for instance, consider a smart building. Here, typically the penalty signal is the price, and an optimal controller like an EMPC controller for the building aims at minimizing the cost related to the power consumption. This would lead to a cost-efficient or minimal solution. However, if the penalty signal is the CO2 emission related to the actual power mix, then the optimal controller would lead to an emission-efficient control. If we disregard the penalty signals, the controllers would lead to an energy-efficient control, since the total power usage is then minimized. Let us now consider how to find the flexibility function. Typically, models used for simulations are rather complicated. Sometimes these are called digital twins. However, for real-time applications, we need a simplified model for the flexible unit, which could be, for instance, a house. Here we are typically using so-called cyber-physical or grey box models. The most important criteria for such a grey box model are the following. We must be able to estimate the parameters of the model using available signals. The model should be simple enough to be able to provide near real-time forecast of the states. Let's now illustrate the complete data intelligence framework for unlocking the flexibility. The figure here illustrates how data from buildings, cities, etc. can be collected and stored, for instance, in a data lake. Based on these data, we are able to identify simplified models like grey box models. These models are then used for development of controllers and solutions for instance, a smart building or wastewater treatment system. In a specific example, we have created a smart house controller for summer houses with a swimming pool. And here we have selected CO2-based control. That is, in this case, the controllers are simply minimizing the CO2 emission related to the electricity used for heat pumps for heating the water of the pools. This figure shows the share of electricity coming from renewables for a small period around December 1st, 2016. This is for Denmark, and at this time of the year, the renewable energy production is almost entirely wind power. Using the described modeling and control technologies, we have implemented a solution for 30 summer houses. It has been demonstrated that by using CO2 penalizing controllers, we are able to reduce the CO2 emission related to the heating of the pools with 15%. In Denmark, around 70% of the buildings are heated by district heating. And the same principles as illustrated for the summer houses can be used for a smart control of heat pumps in district heating networks. Consequently, we believe that we can reduce the CO2 emission related to the electricity use of heat pumps in district heating systems by around 15%, simply by using the described concepts of a flexibility function and related controllers.